Today we will discuss multidimensional persistence. But before we do that, I want to review plus introduce a couple of additional methods. There are many, many ways of looking at one-dimensional persistence. So, for example, we can take a look at our chain. Oops, I forgot to select the pen. So we can take a look at our chain complexes at various times t, and we can map that into the next time t plus 1. Well, that induces a nice linear map on the homologies. So in this case, I'm taking a look now at the linear map on the homologies. Before, we took a look at the matrix at the chain level, but we can also take a look at the matrix at the homology level. And at the homology level, for this very simple example, we have two connected components. So I've got two elements. And then after, in time 1 unit later, I still have two connected components, so I still have two elements in my zeroth homology. And so if I map, these two here, they both go into this single component here, and then nothing goes into this other component. On the chain maps, it's just the inclusion map that we normally do. One can do something more general than that, but we've only talked about doing the inclusion map. In here, it is the map generated by the inclusion map on the chains, but both of these components right here, both of these vertices get mapped into the same component right here. So if I take my element corresponding to one of the vertices, 1, 0, I want to send it to this component. If I take the other one, which would be 0, 1, I want to send it to the same component. So I can also talk about this map here, which we will refer to as the linear map, going from time 0 to time 1, but defined on the homologies. Any questions about that? Okay. Well, if we take a look at our barcode right here, our barcode says that we have one vertex that it will be the representative of the component that lasts forever, and at time 0 we have a second vertex that also ends. And we can talk about the persistence bars and the persistent homologies, and that's also indicated by the rank of these maps as well. So here I've got the map that takes me from time 0 to time 1. I also have the map that takes me from time 0 to time 0. That's just going to be the identity map. So since I've got two components, that rank will just be 2 being the identity map. It's just the number of components. Same thing over here. This would be L of 1, 1. Again, we just have two components, and so we have the rank of this thing is 2. And then at L01, we can see that the rank of this matrix right here is 1 because two components get sent to one component. And we can go back and forth from the ranks of these linear maps on between the homologies. So we can see that at time 0, we can see that at time 0 we have two components, and sure enough, I think we have enough red on the sheet. Let's get a little bit of blue now. So at time 0 we've got two components, which we can see that are H0. So if we take a look at H, there's no L there, H of 0, 0, H sub 0 at time 0, 0 units later, we're going to see that we will be getting two copies if we're using Z mod 2 coefficients of that. And we can see that both via our barcode, so you can see that both via this barcode, as well as it agrees with this rank right here. If I want to take a look at H0 at time 0 but 1 unit later, well, I can see at my barcode I started off with 2 things here, but one of them was destroyed by that edge. One of them was removed when we added this edge. And so we can see that in this case, our rank is just going to be 1. We'll just have 1 component at this particular time that started off at time 0 and existed 1 unit later. And we can see that via this rank right here. And we can also see H0 starting at time 1 and ending at time 1, or if we want to go further than that, we can. But we can see here that our rank right here is 2, and sure enough, it agrees with our barcode. We do have 2 things existing right here. Again, I can replace this 1 with a p, so we can take a look at, for any time p greater than 1. But remember, this thing stabilizes that we just now have the identity map. Since I only had a change of 1 unit of time, we'll just go ahead and do the identity map after this. And so our persistence is that we do have 2, so we have 2 copies of CMOD 2 up here. So that's another way of looking at one-dimensional persistence, is based upon the rank of the linear maps on the homology. Any questions on that? We also looked at, in terms of, so this was the original definition that we looked at, and note that that is equivalent to looking at the image of the HI. So we were taking a look at, if I want to take a look at H0 of 0, 1, then I want to see what existed at time 0. So I wanted to know what existed at time 0. And then I wanted to map it into whatever existed at time 1. And so we then did our map of 0, 1 applied to this homology right here. So so both of these, we only stated this equality before, but it is clearly equivalent to this. And this clearly is actually clearly not the standard math clearly where it takes a day's work to see that it really is clearly true. What we're having is we're taking the things that exist at time I. So we're taking the things that exist at time I, and then we're mapping them into the things that exist p units later. So we cancel out these things here, but we only took what was in our original domain, so the image of our domain of the ith homology, by intersecting it with these things that are killed right here. So both of these definitions give us our persistent homology of at time I and then p units later. We also do have the triangle one. I mentioned the triangle one, but I said you should take a look and see if you can figure out the triangle one. So since we didn't finish that one off, let's take a look at, suppose I want to again we'll stick to this one right here. Well, let me go ahead and take a look at the point 0, 1 where my axis is pointing downward. So this right here is the point 0, 1. If I count the number of triangles that this point is in, I get my homology. So this point, remember, this is a dotted line right here, so it's not in this triangle that was generated by this because it got killed 1 unit later, and so that's why we did a dotted line here and an open circle. Versus it is in the infinite triangle generated by this line, it is in that infinite triangle. And so we can count the number of triangles. It's only in one triangle, and so we can get the homology that way as well. So we've also got the triangle one too. Any questions there? We then had the algebra one, which is actually the easiest way to compute it. The algebra one was to go ahead and take our, oops, we're about to select the pen again. So if we take this map where we take our generators A, B, and C, no matter what time they come in at. So no matter what time they come in, we just list all our vertices. And then we list all our edges, and that gives us our boundary 1 map from our 1 change to our 0 change. And then to denote the time change, we can say that, well, this thing comes in at time 1, so maybe I'll put a superscript 1. These came in at time 0, so at time 0, that's a 0 there. This thing came in at time 1. And then in terms of the boundary, we just put the coefficient of 1 minus 0 is t to the 1, 1 minus 0 is t to the 1, and 0. And I actually did this over arbitrary coefficients, so the boundary of AB, depending upon how you orient it, was b minus a, and so I had a b minus a right here for my boundary. But we kept track of that our edge came in 1 unit later with this t business. That's actually the way we're going to do the multidimensional persistent homology, is with this matrix here as well. We can do similar column and row operations to keep track of when these things enter in and simplify our stuff. So based upon this matrix, based upon this boundary, or based upon the barcode, we can see that we have one generator. I've got my generator A. It came in at time 0, and it went on forever. And so thus I can use the fact that I've got it at time 0, so that's t to the 0. It exists at time 1, so I've got t to the 1, time 2, t squared. And so an arbitrary, if I want to take a look at A at a variety of different times, it would just be a summation with whatever my field coefficients are. We've been working with z mod 2, so we'd have had 0 or 1. But this is to denote that A can last at any time. And so this is what we have, is that A can last at any time. And it came in at time 0. Let's skip over to C. Skipping over to C, we also had that C lasts forever. But the fact that C lasts forever, we wanted to shift it with this sigma 1. So we wanted to do the sigma 1 notation to shift it. And that is also multiplying by t. And so now with respect to C, I want to note that we've got, we don't have C at time 0. It's always being at, if I take my C, I want to note that we're always having that it's at time 1, time 2, time 3, etc. And so we've got this sigma 1 to say that it starts at time 1 and goes forever. Versus here, so that was my C. We also have the B. The B came in at time 0, so there's no need for a shift. But it ends at time 1, and so we mod out by t to say it only existed at time 0. So we have our shorthand notation for our barcode. Instead of, the pictures are really nice, but our shorthand notation will say whatever time we enter, we have this shift notation, and then we have our f of t saying we've now entered, and then however many units later it dies, then we mod out by this t to the d business. And so that tells us that our barcode starts at time e and ends d units later. So our notation here, whenever we've got a barcode, we can go back and forth between the two notations. So between the two notations, if I've got a barcode that enters in at time e, So it enters in at time e, and it dies at time e plus d, then I know that I will be getting that my shift is e, and then I mod out by t to the d. So whether or not you want to work with the algebra notation, it's good to know the algebra notation because then you can go further. But if you just want to relate the algebra notation to the picture, that's actually all you need. So as long as you can relate this algebra notation to the picture, that we can go from here to there, that's all we need. So now we're ready to go and take a look at multidimensional persistence. With multidimensional persistence, we have more than one dimension. So we can do our standard epsilon balls. So we can fix, in this case, our two variables. We have our epsilon changing and our curvature changing. So this is a case when we have more than one thing we're interested in. We might actually want to look to see how our simplicial complex changes as we allow higher and higher regions of curvature. So in the beginning, we have low regions of curvature, but then later on, we allow for more curvature, and we might be wanting to study how our simplicial complex changes with respect to curvature. And we can do our standard one-dimensional simplicial complex by just fixing our epsilon and allowing our curvature to change. Or we can fix our curvature, so we can fix our curvature and allow our epsilon to change. But the problem is we frequently don't know which is the best epsilon or which is the best curvature. We would like to be able to look at all of it, and so we want to be able to allow both of them to move at the same time, but we can do that using the matrix notation. So in this toy example, coming from the paper Computing, got to select the pen. Eventually I will get a laptop where it'll be easier to use the pen, but finding one has been difficult. So we have to select the pen each time. But we basically do exactly the same thing that we did for the one-dimensional case. Suppose I look at the edge AB. The edge AB is going to come in at time 1 with respect to the first dimension and at time 2 with respect to the second dimension. So if I look at the edge AB, here's my A and here's my B, my edge AB comes in with respect to the first dimension at time 1 and with respect to the second dimension at time 2. So we will, instead of using t squared, we're now going to use two variables, x1 for the first dimension and x2 for the second dimension. So we have our x1 for the first dimension as well as our x2 for the second dimension. Our A, however, according to this, came in at time 1 for both x1 and x2. So if I start off, this is the 0, 0 time. If I go over 1 and up 1, or up 1 and over 1, it doesn't matter. I can see that A is created. Remember, in terms of the notation, when drawing these things, a dot or a dot was used to enter in, or a light color was used to say when the complex first entered in. And so I can see that A didn't exist over here, A didn't exist over here, but it did exist here. And so we have that A came in at time 1 with respect to both x1 and x2, so it's represented by the polynomial x1, x2, versus AB came in at time 1 with respect to x1, but time 2 with respect to x2, and so it's represented by the monomial x1, x2 squared. But we do exactly the same thing that we did for the one-dimensional case. we just take this monomial, divide through by this monomial, x1, x2 squared divided by x1, x2 gives me an x2 left over. So it's the same thing we did before, it's just now our monomials are slightly more complicated. So if I take a look at, for example, EF came in at time 1 in this direction, so it came in at time 2 with respect to x1, but we can see it came in at time 0 with respect to x2. And so the monomial for EF would be, since it came in with respect to time 1 for x1, we get an x1 squared, but times 0 for x2, so it's x2 to the 0, or just no x2. And so we have the monomial here is x1 squared. If we take a look at EF, the vertices E and F, they are required to enter in before or at the same time. And so we can take a look at E and F. They actually both entered in at time 0. They both came in at time 0. And so if I take x1 squared divided by 1, we get x1 squared divided by 1, we get x1 squared. So any questions about that? The division will always work nicely because we have to have the edge, the vertices must exist before or at the same time that the edge comes in. So that's how we create our matrix. Any questions on creating the matrix? So very similar to the 1D case. We can now do our column operations. So just like before, we want to do column operations to simplify our object. And so I have my leading entry here, and I would like to get, everything zeros the rest of the way. And so I'm going to want to add column AF and AB and replace column AF with that. So we just go straight here. And so if I do x2 plus x2, I'm doing z mod 2 coefficients now. So 2x2 gives me 0. And then x1 x2 squared plus 0 gives me this. And then we had 1. So we did the column operation, and we now have this new column right here. So very similar to what we did before. Eventually we're going to get into trouble, but in the beginning, let's go ahead and I can see that my leading entry here would be a 1. I can now add that to this column right here. 1 plus 1 gives me 2, which is 0. And so I've got a 0 down here, and continuing adding my columns. So we just went ahead and added these 2 columns and put them into this column right here. Continuing to simplify, I want my column echelon form to be, zeros to my leading entry, so I'm just going to switch the 2 columns. So we'll now just switch our 2 columns, BC and CD, and that gives us this one right here. So now I have my leading entry and zeros exactly the way I want. Let's go to the next one. We're still okay, but now I need to simplify these things here. I've got my leading entry, but in terms of the non-zero terms, if I take a look at now this thing right here, I need things to divide preferably. I say preferably because you don't always get the division. But I can see that this one does divide these other 2's, so I'll just go ahead and move my BF column up over here. So that's to go from here to here, I just move the BF column up, and that way I have a nice term here that divides the other 2 terms. So we've been really lucky with this simple example. We can now go ahead and get rid of this term right here by doing BC plus x1 squared BF. I need to do an x1 squared BF in order to get 2 of these And so that's what we do to go ahead and get this one, is just take this column, do x1 squared times b. X1 squared times bf gives us this. 0 plus that gives us that. X1 squared times x2 squared gives us this item right there. So we've got a 0 there. We can then do something similar to go ahead and use this thing to get rid of this one here. So we now have, if I divide these two, I need an extra x1. So we now multiply the bf column by x1 and add it to this column here. And that actually gets us all zeros since we have the same quantity here as here, x1 times that. So things have simplified, and we're now at this stage. This is where things start getting a little bit interesting. Things can actually get a bit more interesting than this. But we're going to keep to just, a fairly simple example where we're not actually illustrating the full difficulties. But x1 goes into here, so I can eliminate this. x2 also goes into here, so I have a choice. I'm going to choose the one reading from left to right, so I'll go ahead and switch these two columns. But you're probably noticing that there's going to be a problem with this x2. But if not, we'll see it. We'll just switch these two columns to begin with. So switching these two columns. And now I've got my two columns switched. I'm still somewhat okay at this stage. I can go ahead and use this to get rid of this one here. These two do divide. So we'll go ahead and divide that. And dividing it, I get x1, x2 squared. So I multiply it by x1, x2 squared, and that gives me a 0 here, and also gives me an x1 squared, x2 squared. So we've got that. Continuing on. Well, now you might notice a problem. I want my leading entry, and then I would like everything to be zeros. I've got a problem. I can't get rid of that x2. There's just no way to get rid of that x2. There are some times when it doesn't divide, but you can do a generalized division algorithm. It's actually very generalized. You actually create a Grosvenor basis, so things get a little bit more interesting. But because we're working with very specialized things, we do get nice homogeneous polynomials out, and so the algorithm actually does become polynomial time. So I'm only showing you something where actually not much goes wrong. Yeah, we do have a little bit with that x2 business here, so something small does go wrong. But even if more goes wrong, you still have a nice polynomial time algorithm, which actually doesn't always happen when you're trying to simplify generic things when you have polynomials in more than one variable. So when we've got both x1 and x2, the general case is actually quite complicated, requiring exponential time. But because we have very specific homogeneous polynomials here, a polynomial time algorithm does exist. So we're going to temporarily ignore this x2. We will eventually deal with it, but I will note that I can note that this does divide this. So we will switch these two columns here, switch those two columns, and now we can use this column to get rid of that. And so dividing up, we get an x2 squared business. So we've got an x2 squared business here, and that gave us our column of zeros. And now I'll do one more operation, and that is to go ahead and switch. So I'll put the CE column in front of all the zeros, and so now I can have this thing right here where this breaks up into these things here plus our columns of all zeros. So when we take a look at this, we're actually going to want both our x1 and x2 columns. They are going to mean something. So let's take a look at what each of these columns mean. And so we will take a look at this leading entry, this leading entry, this leading entry, and we'll take a look at these. Normally, I wouldn't have called x2 a leading entry, but we're going to keep it anyway. We're going to combine those two, and then we'll take a look at this one here. So let's take a look at each of these individually and see what it means in terms of our persistent homology. So we'll first take a look at our A business. Our A came in at time 1, 1. So in terms of my persistent homology, I'm going to have a shift of 1, 1 in terms of my generator. And then I do have my z mod 2 coefficients with both my x1 and x2. So we'll always have this part here. So this is similar to our it's similar to our ZT, Z2 of T notation. We always have that as long as things didn't fully cancel out. Now with our multidimensional, this is what we will always have. And then we will have this shift if it comes in at a different time. But then we can also mod out by AB, this edge AB came in at time 1, 2. What is the shift? The shift is only in the x2 direction. It's only in the x2 direction, so I only need to mod out by x2. So the x1, if we take a look at my x1 direction, in terms of the big picture, we never had an edge canceling out our A. The only edge we had canceling out was in the x2 direction. We never had an edge canceling out in the x1 direction, only in the x2 direction. So, but in terms of our persistence, once we have this edge AB, it has to exist in everything higher dimensional. So otherwise, if they're multidimensional, this must embed inside here, this must embed inside here, this must embed inside here. And so once we have the AB here, we're going to have the AB here as well. But it came in because of the x2, not because of the x1. And so thus, we have representing our A generator. Our A generator is represented by this shift because it comes in at time 1, 1, but then x2 kills it 1 unit later. And so if you were to take a look at the sort of persistence, it persists quite fine in this direction, but we killed it over here. So we don't have anything going up because we killed it in this right there. Let's take a look at our D. Our D came in at time 1, 0, but it got killed by CD at exactly the same time. So we can completely ignore this one. There's no generator. We kill it right away, so we can get rid of it. It came in. If you wanted to, we could go ahead and say it came in at time 1, 0. We have the Z2 of x1, x2, but then we killed it right away. So actually right away, so we killed the entire thing. And so x1, x2, we killed everything. So everything goes away. So we don't have, Z doesn't persist at all, so we can ignore D. Questions about D? If we take a look at B, now all the other vertices came in at time 0. And notice we did do the descending order, as we did before with the one-dimensional one. And if I take a look at it, it gets killed 2 units later. So if I take a look at just using the matrix, I've got my Z mod 2 of x1, x2, x1, that's a 1, comma, x2, no shift because it came in at time 0, 0. And according to the algebra, I kill it off with x2 squared. Let's take a look at the picture. It came in at time 0. It got killed, according to the algebra, by the edge BF, and so it got killed, so it still exists here, and it exists all along here, so it exists all along here, but it no longer exists for any of these higher ones. You know, the edge BF. The edge BF exists for all the rest of them, so it only exists among, let me actually change the pen color on this one. It only exists among these dimensions here. And we can see that both in terms of the algebra notation, because it says that there's no shift, so it came in at time 0. And we say that it exists forever in terms of the first coordinate, x1. It does exist for one of them, for one x2. It just doesn't exist for the second x2. But in terms of our first coordinate, it does exist forever. So questions on that? So we have, for our B, this one right here. Let's take a look at the C, just so that we can kind of see it in terms of the big picture. We have C comes in at time 0, so it came in at time, this was our C, it came in at time 0. If I now go over and take a look at my C, this was the interesting one. Let me check to make sure I did my C. Yes, I did do my C next. So let's go ahead and take a look at our C right here in terms of this picture zoomed in. So in terms of this picture zoomed in, it came in at time 0, but it got killed in both the first and second dimensions. So we've got our time C, but if I take a look back at where this thing was, it got killed off by my, so in terms of my x1, that pen back.
Question.
Question. Oh, so that was before in the preceding example. So there is still a question in terms of the preceding example as to, for this one right here, for B existing at all times. Is that correct? In terms of here, algebraically, we never mod out by x1. So algebraically, we can see that B exists forever, algebraically. But we can also see that, so algebraically, we can see that B exists forever with respect to x1 because we don't divide out by x1. We can also see pictorially, that B exists for all x1s as long as it exists in terms of the x2 coordinate here. It doesn't exist up here, so there is no x1 up here because there's no x2. We've killed BF, so if it doesn't exist for x2, then it's not going to exist for the x1 squared here either. So it only exists here as well as here. And we can see that pictorially as well as algebraically. We can see that in terms of, if I write out an element in this thing right here, if I try to write out an element x2 cubed times x1, well, that would actually have taken me up one level and over one level, so I would have been above this thing right here. But because of this x2 cubed business, I get rid of it. It doesn't exist at any level above 2 and above. It doesn't exist at any level 2 and above because we know we have this edge. And the edge, though, came in at time BF, at time 0, 2, And because we're required to have this inclusion, if it comes in at time 0, 2, then it must exist at time 1, 2. It must exist, for all the higher x1s as well. But you can see that in terms of the algebra that we cancel it out here. So B does exist for all times in x1, but only for dimensions x2 and dimensions, so x2 having just one x2 or just 0 x2s, but no more than 1 or 0 x2s. Does that make sense? I have a feeling the next example might better illustrate your question, because if I'd modded out by x1 in a different dimension, then you can cancel out B, you will be canceling out C in 2 different dimensions. Yes. So the next example, we cancel out C in 2 different dimensions. So if we take a look at our C, we're canceling out C in 2 different dimensions. If I move 1 unit over in the x1 direction, so if I move 1 unit over, so I start off, there's no shift, so I move 1 unit over, I'm actually canceling it out with the edge DE plus CD. So this DE plus CD, we're going to use that edge to cancel out this one right here. We had already used CD, so we had already used this edge CD to cancel out our D. So we had used this CD to cancel out the D right here. So use this to cancel that out. So I can't use my CD, but I can use my DE plus CD. So if you remember when we talked about the creators and destroyers, sometimes you have to go back a bit more. We can try using the CD, but that edge is already used. So instead, we have to use the edge CD plus DE. And so that's the edge that gets rid of our edge, our vertex C in the x1 direction. Versus in the x2 direction, so we can see we've got this x2 direction right here. That's the edge CE. I know I go up. So my x1 told me to go over. My x2 tells me to go up 1. And so we go up 1, and we can see that CE is getting rid of it right here. And so we can see that in this case, our C naught actually only exists here. Let me get a darker color to write things in. Let's check to see if magenta is a dark color. So I have my Z mod 2 with no shift because C came in at time 0. I've got my x1, x2. But then I mod out by both x1 as well as x2. So I'm modding out by both x1 and x2. Not quite everything, though, because I still have that C naught actually did exist at time 0. And so this would actually simplify to just having my Z mod 2 and only a Z mod 2. So this simplifies that. If I take any polynomial in here, let's take a monomial. If I take the monomial x1, x2 squared, well, because I modded out by x1, this goes away. If I take the monomial x2 cubed, well, because I modded out by x2, this also goes away. The only thing that remains is my constant term, 1. That's the only thing that remains after you mod out. But we do have the 1. Unlike in the D, when we got rid of things right away, we got rid of the 1 too. But in this case, we keep the 1. And you can see how that might have worked if we had moved up this edge into here instead. Then we would have been modding out by an x2 squared instead. So if CE didn't come in at time 1 with respect to x2, If it had come in at time 2 with respect to x2, then we'd have just had an x2 squared. But we'd still have, we can mod out in 2 different directions. So you can mod out in the x2 direction as well as in the x1 direction. And that's why we had to pay attention to both columns. So both columns gave us information in terms of killing C in 2 different directions. Any questions about that? Well, E is, again, so that was our C. We modded out by that. And now let's take a look at our E. Our E is pretty easy. Let's go ahead and zoom in on the next one. So our E, this was our leading entry in terms of our E. Actually, let's look at the bigger picture. It's easier to see that in terms of the bigger picture. So if I take a look at my row with respect to E, now this is my leading entry. We don't need reduced column echelon form, we just need echelon form. So I don't care about these terms right here. They don't bother me at all. I just want preferably zeros here, although sometimes I can't have that. But anything after, I only care about things after the leading term. So when I take a look at, didn't need to do that. When I take a look at my terms here, I take a look at my leading entry and the terms that come after it. I don't care about the before. So here I take a look at the leading entry. I don't need reduced echelon form to see how many solutions I have. I just need echelon form. And so we can see that EF comes in 2 units later in the x1 direction. So I can go in 2 units later in the x1 direction. And so we can see that we will be no shift because E came in at time 0, but we are going to mod out by an x1 squared, which we can see that right here. So we've got this right here for our E. For our F came in at time 0, but do I have any leading entry corresponding to F? No, I've run out of leading entries. I already used EF to kill E. I have nothing that kills off F, and so F lasts forever. So F is going to last forever. If I want to draw the picture for F, it lasts in both the x1 direction and in the x2 direction. It's going to last forever. I can now combine all these terms, and this right here is the shorthand for the barcode. So that's the shorthand for the barcode. And it tells me everything. We looked at what it means in terms of the picture. And so, the algebra notation looks messy. You can do messy things with it if you want, but you can also think about it just what it means in terms of the picture. This right here tells me to shift to start off at the 1, 1 time, so it tells me to stop off at the 1, 1 time, and it tells me that in the x2 direction, I don't want to go up because I've modded out by the x2, and so I just go over here. So the same pictures that we drew before make sense. Now, the easiest way to calculate it, however, is to use a bunch of algorithms, which does give you a polynomial time algorithm as described in this Computing Multidimensional Persistence by Carlson, Finch, and Simorodian. Of course, the easiest way, instead of just using the algorithm, would be to use the computer program Dionysus, and we will discuss that software. I say next lecture 1 week from today. We actually might do an intuitive definition of cohomology 1 week from today. But at some point, I haven't decided which one we will do first, whether we'll introduce Dionysus or the cohomology, maybe both. We'll see, because introducing things via software sometimes is the easiest. But note, I have left off a lot of details as to how to calculate these sorts of things. We only did a very specialized, simplified case. but we can still use this software, and so we'll go over the software. Remember to listen to the IMA lectures on Wednesday, Thursday, and Friday, as well as all of next week. So we will actually, it isn't 1 week from today, it's 2 weeks from today. So we have workshops for the next 1.5 weeks. And so this should be 2 weeks from today. So you will get a blank screen if you come in and see me next week, but 2 weeks from today we will meet. In the meantime, listen to lots of IMA lectures, and if you've got questions that if you're going to attend the workshop, let me know, and we can have a group meeting with the speakers and have maybe a lunch with the speakers as a group. If you aren't attending, but if you want to ask the speakers any questions, feel free to email me the questions, and I will ask the speakers directly. I will be at the IMA for the month. But we will meet in 2 weeks, and I can ask speakers lots and lots of questions. If you've got any, let me know, and I will let them know it's your question, but I will pass on the information back and forth. Any questions?